Hi, it's Romeo Bruni. I'm back after a few months hiatus. I'm so happy to be here and so excited to talk about the Big Bang. The proof of the Big Bang. The Big Bang is not an easy theory to accept. To see that everything was created from nothing is a hard theory to accept. So why? Why do we do it? Well, first of all, the Big Bang is not an origin story. The Big Bang does not describe where the matter and energy in the universe came from. The Big Bang describes the emergence of our present universe from a high temperature, super dense initial state. It makes no claims as to what preceded this super dense, super hot state. It has no idea where it came from. So why do we even go there to the Big Bang when such a thing as everything from nothing seems so incredulous? The reason is the evidence takes us there. When we look at the universe, we see things, and when we interpret those things, they all point to the Big Bang. There are 4 pillars of the Big Bang, which are separate and independent proofs of the Big Bang. Each alone would be significant. Taken together, it's overwhelming the proof, and that's why the vast majority of cosmologists and astronomers believe in the Big Bang. Let's look at the 4 pillars of the Big Bang. Of course, the most important pillar is, and the first pillar was the Hubble Law. George Lemaitre was a Belgian priest who used various parameters to study the universe, including Einstein's field equations, and determined that the universe was likely expanding. Of course, at the time, his ideas were poo-pooed. Following that, Alexander Friedman, using the Friedman equations, which are derived from Einstein's field equations, determined that the universe must either be expanding or contracting, that nothing else made any sense. The big breakthrough came when Edwin Hubble, by measuring the distance of Cepheid variable stars in distant galaxies, determined the Hubble Law. The Hubble-Lemaitre Law is the most important, one of the most important elements of the Big Bang theory. So the Hubble Law basically states that the receding speed of a galaxy is proportional to its distance from us. In other words, the further a galaxy is away from us, the faster it's receding from us. Therefore, when you do the extrapolation, it's obvious that the universe is expanding. Much like the galaxies are raisins in a raisin bread, with the whole bread expanding rapidly, and thus the distance between the raisins, if you will, i.e. the galaxies, increasing rapidly. That is the Hubble Law. The Hubble Law, showing a vastly, quickly expanding universe, obviously, when taken in reverse, leads back to the Big Bang, leads back to a singularity. The fact that the universe is expanding rapidly means obviously it was much smaller and denser at one point. So obviously the Hubble Law is a very important part of it. The present most convincing theory for the Big Bang is termed the Lambda CDM model. Lambda refers to the dark energy, and CDM is cold, dark matter. That's telling us that the universe has more than just baryons in it. It has a very important entity called cold dark matter, which is very important in galactic formation and obviously universal formation, and also has an element called dark energy, which kept the universe from collapsing in on itself right from the beginning, because densities in the primordial stages of the Big Bang were incredibly dense as black holes, so they should contract in on each other, but they don't. It's dark energy that keeps the universe expanding. The universe is expanding. It's not an explosion of matter into an empty universe. Space itself is expanding everywhere. Time and space is expanding between co-moving points. This is the important thing with the Hubble-Lemaitre law. So the Hubble law itself would be convincing evidence. We're just looking out and seeing what we see and then extrapolating backwards. So the Hubble law, number one. Number two, the cosmic background radiation. Anytime, just like Einstein's theories, a theory leads to things in the future. It predicts things in the future that are then discovered. For example, just like Einstein's general relativity predicted gravitational waves, and many years later they were discovered. Just like Einstein's theories predicted black holes, and then many years later black holes were discovered. Anytime a theory predicts things and then they come true, that is very strong proof for the theory. The cosmic background radiation is such a thing. The idea that the universe began very dense and then expanded quickly, when examined in close detail mathematically, predicts that in the first 380,000 years, the energy and density would be so great that photons themselves would not be able to emerge because they would be being scattered continuously within this super dense universe. But after 380,000 years, the universe becomes transparent, and black body radiation would be emitted in the form of cosmic microwave background. So the theory predicted that it should be there, and then the scientists began to look for it. And in 1964, sure enough, Arnaud Penzias and Robert Wilson, when they were looking for something else, serendipitously discovered the cosmic microwave background. And sure enough, the temperature of the cosmic microwave background was exactly what it was predicted to be, approximately 3 degrees Kelvin. And it was, in fact, 2.725 degrees Kelvin. And not only that, but the spectrum around that peak temperature follows the black body radiation curve perfectly, more perfect than any black body radiation experiment we can devise on the Earth. In other words, when they found it, it was like another completely independent sign that the Big Bang did occur. And later, when they analyzed the cosmic background radiation in greater detail and noticed the small anisotropies, troubles pronouncing that word, which are differences in the temperature from spot to spot, the higher temperature areas have gone on to show themselves to be the early galaxies forming. In other words, the picture we got of the cosmic microwave background correlates very well with the structure of the universe as we see it today. So cosmic microwave background, its existence, its sheer existence, the temperature, the fact that it's a perfect black body radiation, and the distribution of the background radiation matches perfectly with the universe as we see it today. So cosmic background radiation, very important. Third big factor, and that's the primordial nucleogenesis. Again, the Big Bang theory predicted that because temperatures were so dense and so high initially, that the hydrogen that was produced by the Big Bang would, in the first short period of time, produce higher elements because the heat was so high. In other words, the hydrogen would produce helium-3. It would produce helium-4. It would produce deuterium, and it would produce lithium-7. And it predicted the amounts of helium-3, 4, deuterium, and lithium that should pop out. And in fact, when then we go to measure the amount of these minor elements in the universe, we find exactly the right proportions between the various light elements, helium-3, 4, deuterium, and lithium, that we would expect. So this is very solid proof, again, completely independent of the other two. There's no other known explanation for the relative abundance of these light elements other than the Lambda CDM model at this stage. So primordial or Big Bang nucleosynthesis is very strong and independent evidence. We can measure the amounts of the elements that are there, and they exactly correspond. The fourth pillar and independent pillar of the Big Bang hypothesis is the difference between the galactic, the universe as we see it today and as we saw it in the past. The previous steady state theory for the universe would have had the universe as seen in the distant past the same as the universe today, because the universe is, after all, a steady state. But what we see and what James Webb Space Telescope has shown is that the galaxy, I should say the universe, more specifically, we're seeing galaxies and quasars in the early universe, would be and should be quite different from galaxies and the universe that we see today. And in fact, that's been shown to be correct. When James Webb looks out, it sees galaxies that are quite different in terms of their star formation, in terms of their size, than galaxies today. So that difference between them and now is quite significant. Also, when we look at the times and distances into the past in terms of the age of the stars seems to correlate very well with the age of the oldest stars, correlates very well with the age of the universe. In other words, the oldest stars seem to be around the same age as the universe is itself, because of course very small stars are going to burn very slowly and they can exist the whole life of the universe up until this point. So Big Bang nucleosynthesis, and then now we're talking about galactic evolution. Also out of interest, when they've looked into the distant past, they've found primordial gas clouds, and these gas clouds have very little metal, very little carbon, very little silicon, etc. in them. They're the result of population 2 stars, and yet they have very little metal in them. And this would correspond with the fact that early in the universe, the stars have not had time to make the metals, so that gas clouds in the early universe should be relatively metal poor. And that's what we've found, that there's differences in the early universe versus the universe at the present time. So it's very simple. We don't choose to believe the Big Bang theory, the lambda cold dark matter theory for the universe because it's convenient. It's not convenient because it brings up the ultimate problem of what came before it, which may or may not ever be solved. But despite that major problem, scientists, astronomers, cosmologists, in the vast great majority, 99.9% probably, believe in the Big Bang because of these 4 independent supporting arguments, each independent, each pointing to the Big Bang. Again, they are the Hubble Law rule constant, showing that the universe is expanding, therefore extrapolating backwards, it must have been small. The cosmic microwave background, which is omnipotent and omnidirectional, a perfect black body spectrum that can only be explained by the Big Bang theory. Big Bang nucleosynthesis, producing exactly the right amounts of helium lithium and deuterium that we see in the present universe, and of course the difference between the universe today and what it was before. There's many articles like this one. No tension, JWST galaxies at greater than Z equals 10, consistent with cosmological simulations. This is saying that the most recent computer simulations using Renaissance and other powerful computer tools are reproducing galaxies in the very early universe, just like what we would predict them to be. So no, James Webb has not found anything that in any way discounts the Big Bang. Yes, it's found things that would make us reevaluate or reconsider how galaxies are formed in their early stages and how quickly. Yes, these are fine points within the Big Bang theory that in no way defeat the Big Bang theory. So yes, believe in the Big Bang theory, and there's multiple reasons, 4 at least, to do so. I'm Romeo Bruni. I hope you enjoyed this. Have a great day. Wow, 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 wow.